let's get started. All right, here we go. So for these problems here, you're asked to evaluate the limit as x approaches infinity and negative infinity, and then state the horizontal asymptotes. Well, essentially what's happening here, if x is approaching infinity and negative infinity for number one, you're basically doing cosine of 0. And what's cosine of 0, guys?
1.
1. So we expect that to get close to 1 as x approaching infinity or negative infinity. It's just getting closer to 1. And it actually is a horizontal asymptote. Be y equals 1. And if you don't believe me, all you have to do is just go to Desmos and type it in y equals cosine 1 over x, and there you go. It's getting close to 1. So that's the whole point of a horizontal asymptote. It's about approach. Not necessarily a boundary that you can't cross. Like, that's totally fine if you cross it. It's really more as x approaching infinity or negative infinity, what does the graph look like? And it looks like a horizontal line. It has a linear behavior to it. So you're going to state that, right? Hey, it looks like y equals 1. All right. I don't want to beat around the bush around that question, so let's move on to 2. For number 2, because the bottom is getting much bigger than the top, in other words, the top has a range, right? So any sine function, as long as you don't have an amplitude change, any sine function, the range from -1 to 1. But the bottom just gets really big, so overall that gets close to 0. So you're gonna say y equals 0 is your horizontal asymptote. For this one, the e to negative x actually joins the bottom, so bottom just gets ever bigger, so that's 0 again. For 4, there is none. Or you say D and E. So no horizontal asymptotes. I mean, if you want to state it in terms of infinity, I guess you could say it's positive infinity when it's going forever towards infinity, and still would be positive infinity, I think. It's going to the left because you have two negatives being divided. So for 5, part A is going to be 3, and part B is going to be -3, right? Because the bottom is positive, but the top stays, could be positive or negative. But for the most part, the degrees are the same. And you have 2 horizontal asymptotes, by the way. That's possible. Again, if you want to see how that looks, just go to Desmos. Desmos, whenever you're stuck, just go to Desmos, just to help you understand things better. The 3x plus 1 divided by abs x. What was the other part again? Abs x plus 2. Yeah, you see how it's 2 horizontal asymptotes? So there you go. And both are going towards 3. Okay. Let's keep on moving. For 6, same thing. Part A will be 2. Part B will be -2. Part C, y equals 2, y equals -2. Here, there'll be 1 and -1. So y equals 1, y equals -1. Even though they're both flat lines, but they're still horizontal asymptotes. They coincide, but that's okay. And here, there should be 1 in each case. And part C is y equals 1. Okay, we're good? For number 8, should be y equals 1, your horizontal asymptote? Or do you get something different? Yeah, okay. Because the plus 1 next to absolute of x in the bottom is negligible. Good? Number 8, yeah. Shouldn't it always be 1? Hold on. Absolute of x. Yeah, you get 1. Yeah. Make sure you punch it in correctly. Maybe if you didn't put parentheses on the bottom. I don't know. Okay, for 20 to 26. Well, the thing is that if you have 1 over x and you're going towards infinity, that's basically 0. And that's 0. So you just get 1 for number 23. Here, you guys have 2 minus 1. And that's just going to be 1 as well. So that's just 1. Here that's gonna be 0 plus 1 and 5. So you have 5. Here you can write as 2x over x plus sine x over x. That's just 2. Here's cos x over x cubed minus 2x cubed over x cubed. That should just be 0 minus 2, so you get negative 2. And for 26, you have x sine x. Notice I'm breaking it up, right? Just being creative with my fractions. That's sine x over x, which is still 0. And that's 0, so you just get 0 for that one. All right. And here, same thing again. You could say positive infinity here. Negative infinity here. 0 here. 3 here. Positive infinity here. And negative infinity here. But you can say D and E for the infinities also, if you want to. So, does that make sense? We're good? All right. Then for this part here, it's more of the same stuff. I guess in this case, you guys kind of know what's up. Any questions you guys want to ask about, you're stuck on. You want to ask about like 9 or 10 or... What do you guys say for 9? You say 1 over root 2? Yeah. Yeah, because when you have root 2x squared minus 3, when x approaches infinity, the minus 3 is negligible, so it's kind of like saying this, which actually becomes like this. And actually, if it's going towards negative infinity, it's actually going to be negative 1/2 for part B. Negative 1 over root 2. And for part, it should be 1 over root 2. Is that what you guys got? Yeah. Yeah, I should have realized that. Because remember, when you do absolute value, when you do square root of a square term, that actually becomes an absolute value. And again, since you're approaching infinity for x, anything connected to the leading term becomes negligible. She's focused on the leading term. So you're going to get kind of the same thing. Well, actually, because it's 4x squared, so it won't matter. So it's actually going to be just 4 in each case for number 10. For here, that'll be 1 times... Yeah, we already did this one. And that's 1. Here, 1 time... Yeah. Actually, some of these are repetitive. Are these the same problems? Okay, then yeah, then you guys should be fine. Number 10? 4. Oh, wait. No. It's infinity. It's infinity. Yes, sorry. Yeah. This is 0, 3, and pause infinity. If you're doing a piecewise function, this would be 0 for number 20. It'd be 0 here, negative 1 here, and D and E. No, 0. That'd be negative. Wait, that'd be D and E. Because graphically speaking, it looks like this. Yeah. The left-hand limit is going towards negative infinity, the positive. The right limit's going to be going towards negative 1. And then here, if you do 21, that's 1, 0. And if you're going towards that 0, that you get negative, yeah, it's going to be D and E. So, because the left-hand limit is 2, but the right-hand limit is 0. Okay. Okay. I think that about covers the homework, so let's get to the notes now. Okay. So we're going to skip squeeze theorem just because I do need a little more time to kind of think about it. I'm not going to put it actually on the test. I'll probably save it for the next unit. But maybe I'll discuss it on Wednesday anyway, just to have that schedule or save it for the next unit. Remember, our test is Friday. Okay, our test is Friday. Yep. Yeah, it should be in schools, you know? Not school, do you? That's the plan. Yeah, because we finished the unit, so we'll review Wednesday. We'll have test Friday. I must have forgot to put it up. Hold on, let me look at the syllabus here. Limits. Yeah, that's the plan. We have test Friday. Yeah, because we have to keep moving. All right. So guys, let's go to part 4 notes. And the last page is actually kind of blank. So I don't think we really need to worry about that. But I do want to go over kind of wrap things up. Let's go over part 4 notes. Here we go, guys. Okay, more on continuity. So use your calculator to help you sketch the graph f of x. What values of x is function undefined? Okay. One thing you could do to think about it, because I'll do an algebraic determination in a little bit, but you could think of x minus 1 as two factors, root x minus 1, root x plus 1, but we'll save that for a little later. For now, let's go to Desmos. Okay, so that's how the graph looks. So it actually looks like it's a transformation of root x plus 1. Hold on, just got a little lost here. Okay, so graph looks like this. If you plug in 0, I know I get 1. You can't plug in 1, though. There's going to be a hole here, by the way. In fact, actually, if I were to, if I plug in 4, I do get 3. It's undefined x equals 1. And again, you could just kind of sketch it, and that sketch trace it. Yeah, see undefined, right? So that's a problem. So algebraically, what you're going to do is get a little creative here. Think of it as root x minus 1 times root x plus 1. And so those cancel. You get 2. Now, using parts A and B, identify the type of discontinuity. We call that a removable discontinuity or a point discontinuity. Explain why using definition of continuity. Well, here's the thing. F of 1 does not exist, right? But the limit as x approaches 1 does exist, right? It's going to be 2. Whenever that happens, or if f of 1 does not equal the limit, we call that a removable discontinuity. Yeah, so whenever the limit exists, but the point does not exist, or the point does not equal the limit, that's a point discontinuity. Right. But if the point exists, but the limit does not, the left-hand limit and the right-hand limit are different numbers. That's what we call a jump discontinuity. Actually, I'll summarize it for you guys when I get to the end notes, because I think I need to have that summary for you guys. Yeah, if we have something like this here, which would be like a piecewise function, we call that oh, what did I just do? Okay. Oh, man. Well, that sucks. Okay. Well, I think you guys, hopefully you guys got it. Yeah, Kate, go ahead. Yes, for remove this continuity, I'll just type it up. If the limit exists, but the point does not, or the point does not equal the limit, then you have a point / removable discontinuity. Okay, cool. Yeah.
In case for the limit, sorry, the point does exist, but doesn't equal the limit, is that one, it's called injustice.
Exactly, right. And we'll summarize that at the end. Okay. And then part D, this is a new one. Write an extended function so that it is continuous. You could do it two ways. You could do it as a piecewise or as a simplified function. So if you do it as a piecewise, you would write like this. First of all, we're gonna write ext to explain that's an extent. So basically, you're extending the function to make it continuous. So if you write as a piecewise, you write like this: x minus 1. This is true when x does not equal 1, or 2 when x equals 1. So what you do is you're filling in that hole. You're plugging it in. That's what you're doing. Or if you're as a simplified function, you can just write like this. Equals just root x plus 1. Because if you just saw this, you would never think this is discontinuous, right? You think, yeah, why would 1 be an issue? We know 1's an issue when we see this. But if you just wrote this, so you can write it two ways. You can write the simplified form, because then you would, ignorance is bliss. You would know that, yeah, it's fine at x equals 1. It's not a problem. So does that make sense? So the extended function, the whole point of it is to extend the function to include any points that were removed or that were not part of the original equation. So we're going to see something similar for this one here. I would factor the top. Yeah. Only for the point discontinuity. We have a hole. Right. Good question. So you can write g of x like this. That's totally a-okay. And then, of course, these cancel. So when you want to find the limit as x approaches -2, just get that, -4. Okay. And the extended function would be this. If you just write like this, say g extended x. I prefer to write in the simplified form. I mean, you can write as a piecewise if you want. If you write as a piecewise, you write the original function and then state the y value of the whole, right? Because the whole has a y value at -4. Because graphically speaking, it's a linear function, of course, right? But when you plug in -2, we're going to put a hole there, right? Like that. We good? Okay, cool. All right, let's move on here. There's definitely a hole at x equals 0 or 0, 3. We talked about this already, right? If you take the limit, that's something we talked about in an earlier section. So if you want to write an extended function, in this case, I have to do it piecewise. Sometimes I don't have a choice. I'm not sure what else to do. So I'm going to write sine 3x over x when x does not equal 0. And that. There we go. That's all. Because I know what the limit is, but there's no point there. So you guys see why it's a point discontinuity. The point did not exist, but the limit did. So that's what's happening.
So on the coming test, we will be allowed to graph these.
Yeah, totally. Yeah, 100%. So recall, what is a continuous function? So remember, a continuous function means f of c exists and the limit equals f of c. So this is for any x equals c value in the domain. So for any x equals c that's in the domain,
X C exists, only x plus c exists, and x c that's x plus c of x.
yeah, that'll be continuous. So that's what you have to look for. Go over.
I would say the function is continuous, and then 0 is a point in that domain, but
So in that case, what we do is we look at the appropriate one-side limits in that case for the continuity part. Yeah, no, the limit does not exist at 0. You're 100% correct about that. But for the sake of continuity, you apply the appropriate one-sided limit.
this is the end of the domain.
Exactly right. Right. Great question, actually. So yeah, that's what you have to consider. So most functions are continuous, as you can imagine, like polynomials, trig, exponential logs, even though there's an asymptote or rational function, but within their domain, you're not gonna have any issues, right? Unless you got some piecewise function, something really weird. And remember all the properties we have for limits. Kind of the same thing applies for continuity. If you add two functions continuous, they'll be continuous. If you subtract two functions continuous, they'll be continuous. If you multiply, divide, whatever, it doesn't matter. Or you even do a scalar multiplication like a constant like k, it doesn't matter. Even the composite. If you have f of x and g of x are both continuous and you plug one into the other, yeah, it's continuous. And in this case, you're assuming g is continuous at f of c, right? So now this is an AP style question. I love this question. This is a great question. I'll give you kind of the quick and easy way. Now I'll give you the more formal way. And actually, I do expect you guys to do the formal way. But on AP exam, if it's multiple choice, I don't want you doing the formality. I want you just getting the answer quickly, right? So the quick and easy way. Just plug 2 in for x and set them equal to each other. That's all. Bless you. There you go. A equals 7. That's it. All right. But formally, what you need to do is you got to go through the conditions of continuity. It does exist. What's that for 2, guys?
2 is 3.
Good. Okay, here. Actually, I'm not sure why I'm even asking the question because you're trying to force the issue of continuity. So I'm not even sure why I even asking the question because we want to force the issue. We want it to be continuous. So let's make the limit happen. So what does that entail? That means that the LHL equals RHL. We know that what that means. Left-hand limit, right-hand limit, right? So limit so what's the left-hand limit? The left-hand limit going to be, guys? Perfect. The right-hand limit's going to be and so in order to force the issue, what does they have to equal? 7, right? And then as the last bit, just to prove that f of 2 equals the limit as x approaches 2. F of 2 was 3, and limit was also 3. That's just as a final check. It's just a formality part. All right, good.
On the AP exam, we do have to quickly,
Okay, so in the AP exam, they rarely ask us the free response question. So it'll be a multiple choice question. And a multiple choice question did it quick and easy, of course. The free response, I mean, yeah, for my test, I want fall away. Oh, yeah, I want that. Because you guys have to understand that because sometimes they might ask that you might ask them about continuity of the free response, perhaps. You just gotta just make sure you can explain it. But rarely a question like this is put in the free response. Usually do more advanced questions. No. Trying to go.
the two ways are basically the same.
Yeah, exactly. Right. One's more formal than the other. Right. Okay, last part, intermediate value theorem. Let me kind of give you the kind of again the quick and easy way of thinking about this.
This is like 1, yeah, right. This is 1 and 10. 1. Let's say it's like 2 and 8. Okay. So here's the question. If x is some number between 1 and 10, then what range can we expect for the y coordinates? Exactly. There's a y, like if I pick some random number, let's say like 6, for example, right? The y coordinate, I know what the y coordinate is exactly because I don't know what the equation is, but do I know that the y coordinate, I know this must be true. Right? I know that has to be true. Because clearly f of 6 has to be between 2 and 8. Because what's my lowest y value here? 2. What's my highest y value? 8. And I'm constricted between 1 and 10 for x. That's why it's called the intermediate value theorem. You're looking at the middle,
The intermediate part, right? So there's a formality that goes with it. I just kind of gave you a kind of a
say sloppy, but kind of just a more layman's term that makes any sense. Just yeah, like here's the best of all that's happening. You know, as long as the function is continuous and intervals close, very important. This has to happen. If that does not happen, you can't apply this theorem. We use an example of how this will not happen. Sorry, why does theorem can't work if we don't satisfy these things? Actually, look at my fucking notes.
that's how you can calculate B. They can be a little better. And now I'm gonna fill out this stuff down below and explain the formalities behind it. Let me do this, guys. This will be good for you guys. Let's see here. Lecture notes.
I can't find any. It was absolutely easy for you. No, I can't, I literally can't put it in. It's literally not right there.
Oh, hold on.
Basically.
Here we go.
Yeah.
Yeah, guys. So why don't you guys simmer on this a little bit? Guys, quiet, please. Thank you. So what if you're not
This is legit for
continuous, right? If you're not continuous, you see there's a gap here. So there's no guarantee that all y values between f and f and b are going to have, right? Even to the c value between a and b, because of the gap, you're going to have a problem. Now here, this does work. Are all y values covered between f and f and b the way it's set up? Sure, it is. But is it a guarantee? No, because of this case, right? So not saying that if you're not continuous, the theorem does not work. It could work, but it's not a guarantee. It's a guarantee when you're continuous, it does work. And so that's the formality of it. If f(x) is continuous on a closed interval from a to b, at any given y value d in between f of a and f of b, there'll be at least one x value c in a and b where f of c equals 1. That makes sense. And that's the formality of it. I believe, and you gotta be closed because what is open, right? And do I know the lowest y value? Like, yeah, right? Like, what this is like 2. What's the lowest y value? It's like 2.00000000001. I don't know. Right? So you have to be closed well. In addition to being continuous. Thanks for that. Okay. So and again, it says it right there as well, the formality of it. So now let's actually apply it, write our conclusion, and then we'll kind of just do a summary at the end. All right. So IVT is for short intermediate value theorem. So here's the deal. This is a polynomial equation, right? Proves this has at least one solution. Now, I mean, if I were to graph it, I mean, I'm pretty sure they're going to touch, right? That's y equals x. X cubed minus 2 looks like this. I'm pretty sure they're going to touch. But sometimes when you just see an equation that looks kind of weird and you don't know how to solve it algebraically, in fact, this is not factorable. And I think the answer is kind of funky. Then we're not really sure. But what you can do is rewrite the equation so you have 0 on one side. So let's rewrite like this. 0 equals x cubed minus x minus 2. And we'll let g of x equal that equation. Okay. So what we want to show is you want to show that g of x equals 0 has at least one solution. Okay. So is g of x continuous? What we define as g of x. Is that a continuous function? Yes, polynomial. Sure. Yeah. G of x is a polynomial function, so it's continuous. Okay. Now what we're going to do is let's pick a range of x values. One that provides a positive y value, one that provides a negative y value. So for example, let's make a little table that helps. What if x were 0? What's y? -2. Okay. What if x were 2? 4. Okay. So is it continuous from 0 to 2? Sure. Actually, let me back a little bit. I think what they meant to say here is that since continuous on that, it's continuous on that. And hold on a sec. So let me take this back. Hold on. I'm trying to understand what they're trying to see in this step here. I'm a little confused. Well, so since g of 0 equals -2, and g of 2 equals 4, then there's at least one x value in the interval from 0 to 2 for which g of x equals 0. I know I didn't quite follow the blanks. I apologize about that. I'm just a little confused why those blanks are set up that way. I did already.
Well, I mean, it's inherent. I mean, obviously, zero is I don't know. It's implied. It's fine. But you do have to state your continuously closed. Yeah, so in general, as applied IDT, you must write continuity statements. State that after the A is less than B is less than B, or whatever, and quote the IDT and make sure you prove your ask. So
That's the way you can write it. Good.
Continuity, which you like. Proof about type of C existing.
Not necessarily. I think as long as you say it's if it's a polynomial, you kind of establish that whatever function is. I don't think it's trig or whatever. Not necessarily. Was there a question, Catherine? Yeah. You don't have to go through the whole formality of it. Carl, go.
Do you have to like explicitly state?
Yeah, you do. Well, actually, no, because you already stated right there. That's implied. Because I did write closed interval from 0 to 2, so it's fine. So that's implied, but the continuity, yes, you do have to state 100%. So that's IVT. You'll have a chance to practice on the homework. Just some quick summaries here before we end our class today. Remember, actually, let me pull this up. Again, this is the advantage of having taught AP Calculus AB. I got all these old notes I could call up here. Yeah. You may want to put this in the last page of your notes. So types of discontinuities.
we can use either term, doesn't matter. It means the same thing, they're interchangeable terms. And if you have a point floating or point just is not there, either way, we'll call it a point and remove this continuity.
And from a continuity or formality perspective, the limit will exist. I'll call it C, by the way. But what's going to happen is that FC may or may not exist. And definitely that'd be true. Assuming that if one held true, only consider the third condition.
The first one holds true. Like that second graph, FC does exist. So the second graph, does it satisfy the first condition? Yeah. Does it satisfy the second condition? Yeah. satisfy the third condition? No. Here, this is satisfied the first condition, this is satisfied the second. So seconds are always favored for, point of room discontinuity. It's the first and third unknowns.
Yeah, so that's one way of looking at from a formal perspective. So you want to add that to your notes. Now here, we call that a jump. Because the graph jumps, right?
That's also the fourth one as well.
Sorry, is that?
That's also the fourth one as well.
No, fourth one's infinite discontinuity. That's a different one.
Slates for off.
We'll talk about it in a sec, yeah. So for this one here, FC may or may not exist. But for sure, this one's out. Implying that the limit as x approaches c of f of x does not exist. We pulling that? Then here, we call this an infinite discontinuity. Or basically a vertical class. We already talked about this, but it's just good to talk about it again. And what happens here is that, and the FSC could exist, just so you know. You can actually put a dot here if you wanted to. You can make a piecewise function. That's totally could happen. FC may or may not exist. But what really makes an infinite discontinuity is that the limit as x approaches c from the left and or the limits, it doesn't have to be both because it could be a piecewise function, is plus or minus infinity.
There's an infinite nature to the limit. And of course, the third state is talking about. So,
the last one's called an oscillating. Don't worry about it. It's not an AP exam. I don't care. Don't worry about it. Yeah, it's just because you just don't know what's going on. It's just going kind of crazy when you get close to zero. So just acting weird. Ryan, go ahead.
These numbers, these are things that we can write down like steps. By the way, are these like conditions of?
The conditions of continuity, exactly. That you see up above here.
If it meets those, it means that it's.
If you meet all three, it's continuous. And Oliver, to answer your question about like root x, yeah, you apply the appropriate one-sided limit if it's the limit does not exist. Like root x doesn't exist at zero, but the appropriate one-sided limit as x approaches zero from the right does exist. So okay, I think that kind of closes the loop on all this stuff. So homework, what I want for you guys to do for homework, I'm gonna have you do section D. I think section A. Wait, no, sorry. This is the review. That's review for tomorrow. For Wednesday. I think I'm gonna have you guys do. Yeah, sections A and D actually, of the handout C. So if we look at handout C. Yeah. Yeah, I want you guys doing section A. Yeah. Yep. All section A. And then the IVT one, all section D. Yeah, that's the homework. Yeah. Yeah, I'll post it to School G.